So, what we are talking about today is the harmonic oscillator. And technically, we already did a bunch of work with the harmonic oscillator. That worksheet we did last time, the wave functions I gave you were harmonic oscillator wave functions. So we've already seen how to normalize harmonic oscillator functions, how to show that they're orthogonal, and we've shown that they're solutions to the Schrodinger equation. But let's get to not the mathematical kind of like hammer tool thing. Let's talk about what's actually happening with the physics in that problem and how we get to those functions that are solutions and what the Schrodinger equation looks like. Now, for us, this is really only the second problem we've done. Right? We did the free particle. We did the particle in a box. Both of those were just kinetic energy with no potential. Here, we're looking at our second problem, which is really, this is really only our second problem, our second category, where we actually have a non-zero potential energy term. So if we're thinking classically, the classical picture of a harmonic oscillator is you've got some wall, something that's like super massive. You attach a spring to the wall, and to the other side you attach a mass that's got some mass m1. This spring has some characteristic length. Its rest length is L0. And what we want to do is we want to know, okay, what's the physics of how this thing moves? And you know, if we compress it or expand it, the potential, the force that we should feel should be related to that. Whether it's a restorative force in one direction or the other for the force, or if we're just talking about the potential energy, it's going to be an equal amount of potential energy either way we change it. If you're interested in the classical physics of this, this is Hooke's law. Of course, since we're doing the quantum mechanics rather than going through the force derivation, I'm just going to tell you the potential for this in terms of x would be 1/2 kf. I'm gonna call this. I'm gonna write it like this for now. Kf x squared. And I'm gonna tell you that this x squared is a trick, because really we should think about how far we displace this L from the equilibrium length. The spring's always related to equilibrium length, but we're gonna define L minus L naught squared equals x squared. So we're essentially just redefining our coordinates in a way that's going to essentially set the equilibrium length to 0 and say, look, the equilibrium length in this idea of stretching the spring out is buried inside here. Kf is like a force constant. So that's going to give us an idea of how rigid the spring is. A bigger force constant means that that spring is tighter and going to spring back harder. A weaker force constant means it's a little more slinky-like. Stretches out a bit more. But this gives us a new potential. So now when we look at our Hamiltonian for this system, we're going to have kinetic energy operator plus potential energy operator. And in this case, we're actually going to have something for our potential energy. We're going to have our p hat x squared over 2m for our kinetic energy. And now we're going to have a 1/2 kf x squared for our potential energy. This is completely different from what we've done before. This means that, I mean, it's not completely different, but it's a different problem because now we have this non-zero potential, which means the energies are different. The wave functions are different. The way that we think about the averages, we're still going to think about the averages the same way, but they're not going to be the same as the previous problem. We're looking at a different problem. If I wrote out this operator completely into the Schrodinger equation, we would have negative h bar squared over 2m d by dx squared on psi plus a 1/2 kf x squared on psi equals E on psi. And you can probably already see how I did some of my rearrangement from last time on the worksheet, right? That's why I had that extra factor of 2m h bar over here I had to multiply through. And then I just collected everything in here to make a variable that I called a. And I want to do it the way your book does it, so that way if you're reading along in the book like you should be, you don't get too confused. The way your book rewrites this is d by dx squared psi plus 1 over alpha squared x squared psi equals E psi. Wait. No way. QM h bar squared E psi. We have to collect, we still have to keep that term there. That's got to be there still. Yeah, I totally lost that in my notes, even though I was like, I got to make these notes to make sure I don't mess this up. They define alpha, to set up the problem this way, they define alpha as h bar squared divided by mkf, that force constant, all to the 1/4. Now there's arguments for the way that I set it up, where I had like an a squared there, versus the way that the book sets it up with this 1 over alpha squared. The reason they do it in the 1 over alpha squared for this case is, again, because they have some idea of what the answers are going to look like. And they know that when we start plugging in solutions, when we start taking derivatives, we're going to end up with a 1 over alpha twice. And so they can use that information to simplify things. I like setting mine up a little bit differently, like we did on the worksheet, because I feel like it looks more like our typical differential equations. But at this point, this equation is actually what we would call non-trivial to solve. When we are dealing with a situation where we have a derivative and then we've got some extra x term, this is not something that we would just guess an answer to. This is something that we would actually have to go through the proper methodology of solving a differential equation involving a power series expansion of possible answers, and it takes quite a bit of work to get to it. And I will never ask you to do that. What we will do is we will look at the answers and we'll say, how can we use these answers to make sense of how this thing would behave, using some of the same logic for this same logic we used on the particle in a box for this different problem. So the wave functions that we get as a solution are going to be labeled with some limiting factor v. Just like we had for the particle in a box, we had some counting number n when we applied our boundary conditions. Same thing happens here. We've got some normalization constant. We've got some special function here. Notice not curly h, this is just straight h. I gotta remember how they do this. X over alpha. E to the minus x over alpha squared divided by 2. These functions are solutions. Now, you should all ask the same question. What's that? What's that thing? We know n is the normalization constant. We always use capital N for our normalization constant. This is going to be a Gaussian-like wave function. This is e to the x squared. We've got our alpha, which has some of the physicality of the problem buried inside of it. But this thing, this is the new thing. And this is some polynomial that comes out. And we've got a set of polynomials. So using some generic variable y to talk about this, your 0 case would just be equal to 1. Your H1 case would be equal to 2y. Your H2 case would be equal to 4y squared minus 2. Your H3 case would be equal to, and you don't need to, you can just pull out your equations sheets. Oh, if you don't have the energies and equations that I handed out as well, these are on there. It's worth it to copy them into your notes, but these are not things I expect you to remember. These are things that will be given to you. 8y squared minus 12y. And then it keeps going up. Oh, sorry, not y squared, y cubed. I knew I made a mistake because it should go even, odd, even, odd. So I knew this one should be odd, so I needed that y cubed y. And that's particular to these polynomials. So this gives us kind of the thing, the set of functions, and then we could keep going. These functions are solutions to this equation up here in green. The way that these are figured out is by doing a series expansion and then solving for the different coefficients that are needed in front of, you know, your y to the 0, your y to the 1, your y to the 2. We could go through that, but what's more interesting to us is to see how we can use this information to talk about something, to talk about the motion that results and the probability of it. If we plug this function into our Schrodinger equation, our Hamiltonian, we will also get an energy term, which also depends on V. And that is going to be V plus 1/2 h bar omega. Where I should put the definition for, I'm going to put the definition for omega right here. Square root kf over m. So again, omega is another, it's kind of like your vibrational frequency. It depends on the spring constant and the mass. And then our energy is going to be related to which vibrational mode we're looking at, how much we're stretching the spring, and its characteristic frequency, depending on its mass and its spring constant. At this point, we could go back and look at that worksheet we did last time. You know, I'm not going to ask you to derive these equations, these Hermite polynomials, and this solution. Really, what we want to do is we want to be able to use these. We want to be able to take these functions and be able to calculate the average momentum, average position, average momentum squared, average position squared, the energy eigenvalues, which are given to us, and talk about how this can give us some physical meaning. Now, this doesn't yet really apply to what we see in chemistry, because in chemistry, we don't have masses just attached to a wall. When we look at chemistry, we've got masses attached to other masses. We've got two things that are moving. So if we want to look at, instead of looking at this, we want to look at two masses, we're going to make just one kind of adjustment to this that's then going to work for two masses. Are you ready? Do you have questions yet? So at this point, if we had more time, this is the point where I'd say, pull out your worksheet again. Let's keep working on that. Let's make sure we know how to use these functions. But last time you all did quite well with that. So you're already pretty good at working with these functions, actually. You were able to calculate, oh, let me tell you one more thing. I made you calculate the normalization constants. That is also given as an equation. All of these have a known normalization constant, which depends on that counting number v. Equal to 1 over alpha pi to the 1/2. This is the notation the textbook uses. 2v, v factorial to the 1/2. So if we went through, if I was feeling quite malicious, I could make you normalize 6 or 10 of these and then get you to start recognizing the pattern. I don't know if you'd recognize 2 to the power of v times v factorial in the pattern, but there is a pattern to that. Same thing with energy. The energy pattern is a little bit easier to see. The energy pattern is you just increase by 2/2 each time. So if you remember, if you did that part, if you calculated your eigenfunctions, the first one had a 1/2, the second one had a 3/2, the third one had a 5/2. And you had that constant kind of like increasing. And that we see here. And I could make you do more of them until you really see the pattern, but we get the idea. And we've also got a midterm next week, so maybe you will do more. Question?
What would be the purpose of normalization with respect to springs?
So the normalization constant. So remember, with respect to springs, when we start solving this, this is still going to give us a probability distribution, right? So when we start bouncing this spring, it's going to be moving some. And we want to talk about where are we likely to see it moving, what's our expected position, what's our expected variance in that position as this thing is moving. Now, it's not moving in our straight linear case anymore. It's now got this x squared term that's going to change the way it moves. This what we would call a restorative force based on the displacement is going to get pulled back to where it was before, but it's actually going to overshoot and kind of have this kind of oscillatory motion. So we're still going to look at this function. It's still going to be a probability distribution. And our normalization constant is, again, normalizing to 1 or 100% probability in our bounds of the problem. And again, we have to be careful about physical reality. This might be easier to represent when we go to two masses. Are we ready to look at two masses? Okay. So when we go to two masses, when we change this, and instead of looking at a spring on a wall, if instead we look at two masses, we're going to have the same kind of setup. We're going to have mass 1, mass 2. We're going to have some characteristic length of our spring. And just a heads up, any place I'm saying spring, you can also think the word bond between two atoms. And we'll talk about that in just a minute. Mass 2 will be displaced by some L2. Mass 1 will be displaced by some L1. But we'll call this overall thing. So we can look at all of this with the different masses. And essentially, if we rearrange, we can replace mass with this idea of reduced mass. Essentially saying, as this thing moves, depending on how big the masses are, there's going to be this kind of idea of a center vibrating still, relative as the two masses move. That reduced mass is mass 1 times mass 2 divided by mass 1 plus mass 2. And if we do that, our relative position idea, our relative position actually still just stays a relative position, but this time it's based on L1 minus L2 minus L0. We've got a different relative position, but we can still just treat it as some variable x relative to where that center of mass is, where that mass is kind of vibrating back and forth. If we do that, the only thing that really changes is every place you see a mass, you replace it with a mu, a reduced mass. That's what you would do. And I think I suggested you do one of these problems, but I can also show you real quick if mass 1 is much, much greater than mass 2, take a moment, figure out what the reduced mass is equal to. Mass 1 is much, much greater than mass 2. Really big number plus a small number is approximately really big number. So the first step is we're going to have the top we can't really figure out yet, but if mass 1 is much, much bigger, then mass 1 plus mass 2 is approximately mass 1. Then if I cancel that out, I'm just left with the one mass. Essentially, if this first one is giant, it acts like a wall. It doesn't move, only the other one moves. But as that wall shrinks down to a realistic size, we get this reduced mass for figuring out, like our vibrational frequency is going to depend on the reduced mass. this alpha parameter is going to depend on the reduced mass. And since the vibrational frequency depends on the reduced mass, the energy is also going to depend on the reduced mass. So we just have that tiny little tweak. And then we're dealing with bonds. We're actually now looking at, you could look at H2 if you wanted to do the simplest thing, hydrogen diatomic. You can look at the bond length. You can look at its vibrational spectroscopy. You can look at its vibrational spectroscopy. And based on the different vibrational energies you see, you can figure out its reduced mass. You can figure out its reduced mass, or you can figure out its spring constant. And from the spring constant, you can get an idea of that bond strength. How flexible is that bond between two hydrogens? And then we can start extrapolating. Hydrogen's pretty easy. Your masses are equal. And then as you change your masses, you can start looking at hydrogen with an oxygen hydroxide. You can look at carbon monoxide. You can start changing the things you're looking at, and you can look at how that bond behaves. Now, there's of course a problem with that. What are the boundaries of this problem? What's the limit to our lengths of spring? Now, this is funny because when we look at this, we write it down as negative infinity to infinity. This works out because we've got this Gaussian exponential here, this Gaussian function. As we go to positive infinity, we're going to have e to the 0. This is essentially, sorry, we're going to have e to the negative infinity. This is going to crash out. As we go to negative infinity, that's still just going to be e to the negative infinity. This is going to crash out. So this Gaussian function here, Gaussian functions are incredibly useful. They have easy integrals, and they also are really well behaved. So Gaussians are great. But this is going to make it so this is actually going to be a valid boundary range because this is going to crash out to 0 faster than the Hermite polynomials are going to grow and shrink. So what's the physical problem with saying our bounds are negative infinity to positive infinity? Yeah?
Your spring constant is going to limit how far it can stretch.
Right. So if this is the boundary of our problem, you can imagine your two masses on your springs and say, what if we separated those two by an infinite distance and made the spring stretch an infinite distance? Not going to be physical reality. So the question we might ask is, how well does the harmonic oscillator fit to what we would expect? If we look at a harmonic oscillator, it's pretty much kinetic energy with an x squared term. So I can look at this. Pardon my drawing. I will do my best to make this reasonable. So if we looked at a harmonic oscillator, we'd see something like that, where you can look at your V equals 0. Oh yeah, also, weird thing about this, I should mention this someplace really explicit as well, because we've got this different equation that we're solving, the limits on our number, our quantum number, are going to be different. It's still integer values, but one of the really fascinating differences is it actually has a 0 possibility. So we can imagine V equals 0. Notice, though, at V equals 0, we still don't have 0 energy, and we don't have a 0 wave function. We still have a function that's just going to look like a Gaussian, but we don't hit the bottom of this. Ooh, I can clearly see I didn't make this symmetric, as I should have. I'm going to try. It's about there. I was a little bit off. The Gaussian function, if we plotted this, would look something like that. I would encourage you to look in your textbook. Your textbook actually has some really fantastic pictures of what the different probability distributions look like. So this is your probability. This is your Gaussian squared. You just get an e to the x squared over alpha squared. This is your probability distribution. Your textbook has some really fantastic pictures that are drawn better than I can draw. Now, this is the ideal case, the harmonic oscillator. which I often abbreviate just HO. The problem is, if we looked at a real molecule, if we looked at something that was real, we would get something that kind of looks like this, but not quite the same. So I did my best to represent this. The real molecule follows. This is actually the reason I put real molecule in quotes is because this is an approximation. This is called the Leonard-Jones potential. Yeah, that's right. I always think it's wrong. It seems like a weird name, but yeah. So this one jumps faster as you go to as you start to scrunch down that spring. Essentially, your spring trying to push the two nuclei into each other. That force gets bigger, much faster than the harmonic oscillator would predict. Also, as you stretch the spring apart, you hit a breaking point, right? You pull two nuclei away from each other, eventually it just falls apart. But if you look, as long as we're down here, and I shouldn't put these here quite yet, as long as we're down here, as long as we're down in this region, at the bottom of this curve, so as long as we're down at low energy values and we're not displacing the nuclei too much, the harmonic oscillator actually is a really good approximation. As long as that displacement isn't huge, as long as we're just doing little displacements, you actually get pretty reasonable answers using the harmonic oscillator potential rather than using the Leonard-Jones potential, which is like a 1 over x 6th to the 6th minus 1 over x to the 12th, if I remember correctly. I haven't looked at it in a while. But there's some potential that does this. It's more complicated, it's more realistic, but then we have to use a completely different set of answers to do it. So simple harmonic oscillator works well, though. It works very well for a lot of our diatomic gases and other molecules, as long as we're not putting in too much energy or taking too much energy out. Questions? Okay. Let's see. There's two more things I want to mention before we wrap up. The first is a note about these energy values, and particularly looking at the difference of two energy values. So if we look at this system, if I looked at a change in the energy values, I would be looking at something like EV plus 1 minus EV. So I'm looking at the higher minus the lower. I'd be looking at a difference. I'm just looking at the difference between the two nearest values. If I do that, I would have V plus 3/2 minus V plus 1/2 H bar omega. So essentially, instead of having my energy be V, my first energy would be V plus 1, that's V 3/2. My second energy would just be the V plus 1/2 H bar omega. If we do the subtraction, the V's cancel out. A factor of 1/2 cancels out. And we just get the difference in energy is H bar omega. It's essentially this, this term, which we can then extrapolate even further. Say it's H bar square root KF over mu using reduced mass there. Now, we can actually start to do some simple spectroscopy, right? Our vibrational spectroscopy, this is going to be in the IR range. We can actually start explaining some of the things you've seen in your IR spectroscopy based on how the bonds are vibrating. You all remember IR spectroscopy? Is it like burned into your brains? 1 through 5, IR spectroscopy. You know, and I know the way that you learned it was, oh, this is the OH stretch here, this is the C stretches, this is the CH region, we don't worry about that region, there's too much down there. We can actually get, for simple molecules, we can model it this way. As we get to larger molecules, we're going to have to do things that aren't just like 2 masses. We're going to have to look at how 5 masses attach to springs. And we're going to look at that in, again, approximate ways, how we can